Hello everyone. In the previous session, we have come across the swing equation, and in this session, I am planning to cover the power angle equation, power angle curve, and the equal area criterion. So let me recollect. The swing equation is Pm minus Pe is equal to h by pi f d square delta by dt square. So this is the swing equation, and here you have two power terms. One is the mechanical power and the other is the electrical power. And the equation that relates electrical power with the angular displacement of the rotor. So the angular displacement of rotor is delta. So the equation that relates both PE and delta is known as the power angle equation. For writing the power angle equation, let me consider a sample system where I have two buses, bus number 1 and bus number 2, and these two buses are connected by a transmission line which has a leakage reactance of, line reactance of X12. So here between bus 1 and 2 there is some electrical power getting transferred, right? So let me write that, and before I write, let the voltage of bus 1 be V1 angle 0 and the voltage of bus 2 be V2 angle delta. So under this case, the amount of electrical power transmitted is given as V1 V2, where V1 and V2 are the magnitude of voltages divided by X12, the magnitude of reactance, into sine of delta. So delta is the difference between the phase angles of voltages. So it is the difference between the voltage phase angles of bus 1 and bus 2. So this equation defines the relationship between the electrical power generated and the angular displacement of the rotor. Now, having this relationship as a basis, we are going to draw the curve. So here we have seen PE is equal to some constant into sine delta, right? And this constant value is said to be the maximum power that could be transmitted through the transmission line. And you also call that maximum power as the steady state stability limit. So it is written as P max sine delta. So whenever you have an equation like phi sine omega t or phi sine theta, you so you draw a sine waveform with the maximum amplitude of phi. So this is how we go for drawing this 5 sine theta, right? So similarly, we are going to draw one similar curve. So for this, let me draw the y-axis where I have power, and along the x-axis I am going to consider angle. So you have power along y-axis and delta along the y-axis. So this is a sinusoidal function with the maximum amplitude. So the maximum amplitude P max. Okay, so with the maximum amplitude, so draw a sine waveform. So you have only the positive half while you consider for a generator, and while you are drawing for a motor, you will be drawing the same characteristics along the negative y-axis. So if you're going to consider the sinusoidal waveform, so the curve on the positive side denotes for the generator's power angle curve, and the negative is for the motor. Your motor is consuming power, and hence you say the power is negative because of consuming. Okay, so you have it along the negative y-axis, and you also have one more power, which is the mechanical power. So we have drawn the power angle curve, but here on this same curve, let me accommodate one more person who comes in the swing equation, who is the mechanical power. So this mechanical power is not going to be dependent on the value of delta. It is independent of delta, and hence it is always a straight line. And we might also have a question in our mind, like we have a synchronous machine, right? So which has, let me consider a salient pole rotor. So if you consider a salient pole rotor, this rotor is going to make a definite angle. So if this is the rotor's axis, so that's going to make a definite angle when compared to the stator's magnetic field. So this is the stator's magnetic field, so that's rotating at synchronous speed, and this is rotor's magnetic field, which is rotating with the speed of the rotor. So between the stator magnetic field and rotor magnetic field, always I have a constant angle delta, or you could also call it as delta naught. Okay, so if you have a constant angle delta naught, so where do I have the delta naught along this wide x-axis? So that might be a question in most of us. And now let me tell you. So it is at this point, the point that corresponds to the intersection of PM and PE is delta naught. So how do I say that? So when you look at the equation, so let me discuss equal area criteria a little later. And when you look at this equation, the swing curves equation, the swing equation PM minus PE is equal to H by pi F, right? So H pi F are all constants. So let me, for instance, remove this. Okay, so that's proportional to d square delta by dt square. So I could say that PM minus PE is getting reflected as the rate of change of uh, the squared rate of change of delta. So which is acceleration. So I generally write PM minus PE as accelerating power. And now let us look at this point named A. So at point A, PM is equal to PE. So the yellow color line and the black color line intersect each other, which means PM and PE are having the same value, which means PA is 0. That is, when your rotor angle is fixed at this point delta naught, your rotor is neither accelerating nor decelerating. That is, rotor is rotating at constant speed. So the point of intersection between PM and PE is the stable operating point. Okay, so that's where your rotor does not accelerate, and it's where my rotor is going to run at a constant speed.